Kalyan, what you can start.
Okay, sir. Good afternoon, everyone. I'm Dr. R. Kalyani, Associate Professor of ECE Department. Would like to introduce today's speaker. We are honored to introduce Dr. Abhishek Kumar Gupta, a distinguished researcher and an educator in modern wireless communications. Dr. Gupta earned his BTech MTech dual degree from IIT Kanpur and completed his PhD in electrical and computer engineering from the University of Texas at Austin. He is currently an associate professor at IIT Kanpur, where he leads the Modern Wireless Networks Group. His research spans stochastic geometry, 5G, millimeter wave, terahertz vehicular networks, and molecular communication, making him one of the most influential young scientists shaping next generation wireless technologies. Dr. Gupta has received several prestigious honors, including the IIA Young Engineer Award, Class of 1986 Young Faculty Fellowship, and recognition from IEEE Wireless Communication Letters. He is also the author of impactful books such as Introduction to Stochastic Geometry and Numerical Methods Using MATLAB. Before joining IIT Kanpur, he worked with leading global organizations including Samsung, Research America, Future B, Applied Microelectronics, and Nokia Networks, contributing significantly to advanced communication standards. With his remarkable blend of academic excellence and industry insight, Dr. Abhishek Kumar Gupta is truly a leading voice in India's wireless research community. We are privileged to have him with us today as we explore V2X beyond 5G trends, technologies, and future directions. Over to you, sir. Thank you, sir.
Hi, thank you for inviting me for this lecture. I hope you can see my screen and you can hear me well. If there is any problem with the connectivity at any time, please let me know. In today's talk, I would like to talk about our recent work where we have been working on finding how the performance of Platoon networks can be for vehicle-to-vehicle connectivity in sixth generation and future networks. So let me start with saying that, so as we see every day, we have been making a lot of advancement in transportation, and nowadays you can expect that there's a lot of intelligent transportation system being designed in at least these big cities. And the main reason is that there's so much congestion and that there is a requirement of planning this traffic intelligently. And we have been seeing like a lot of technology in transportation also. For example, nowadays people are designing these autonomous car vehicles which can travel them by self. And then car are also having new and new sensors that they can sense around them. They can find out where the nearest vehicle is, and such kind of thing can actually help in their help them in collision avoidance and their safety. And all of us have actually used Google Maps, right? So compared to the previous decade where we usually go to a place looking at the map, now we use Google Maps to go even to a nearest part of the city. So a lot of the dependency is there on this Google Map, and so your vehicle require a lot of data to actually efficiently move around the city or move around the country. So this basically gives us a very interesting thing that if you want to scale our systems with scale our traffic system along with as the vehicles number is growing, as the population is growing, we need to do it a lot with in a smarter way. And the key is actually vehicular communication. If vehicle can talk to each other or talk to the overall network, you can hopefully design things where such can be efficiently managed. Right. And the vehicle communication we are talking about can take various forms. One example is vehicle to vehicle communication, where one vehicle is talking to a nearby vehicle. One example can be just to sense where the other vehicles are, what is their speed, so that they can adjust their own speed to avoid any kind of collision. Another one can be vehicle to infrastructure network, which can be used to download any kind of critical data. That includes the traffic updates, right? The critical alerts, like any kind of accident if has happened, or any environmental disasters like flooding of the roads. Right, along with the entertainment data, like if you want to listen to music or any kind of news while moving. Right. So uh, that's kind of vehicle and when so along with this V2V vehicle to vehicle and vehicle to infrastructure, you can also talk about vehicle to everything communication, which basically means that vehicle can connect to infrastructure, vehicle can connect to the nearby sensors, right? And everything you can imagine they can be connected. In such connectivity, right, you can improve road safety. For example, if you do a real-time exchange of data between between the two vehicles, you can avoid any kind of collision between them because you can adjust your speed preemptively so that the vehicular distance between each other can be maintained. Right, and also you can get a real-time warning if some road is not in a good condition ahead, or there is a flood on the road, or the traffic is really bad, so it may suggest you to take alternative routes. So, right. So, in general, it's not very surprising that vehicle communication will play a very major role if you want to design smart transportation in urban setting, in the future setting. You would like to use them, right? And one such example where you can use such kind of technology to improve your road congestion and other thing is vehicular platooning, right? So vehicular platooning means that the vehicles are actually moving in group. Usually, normally, every vehicle is free to move on their own. They can choose their own path and can move. But this vehicular platooning is a system where you have to follow a platoon, right? So you can divide your overall route to the small segments, and the segments, every vehicle who are taking that segment has to share the route, right? And the benefit of that is all the vehicles are moving together. It can reduce the traffic congestion, right? It can improve in the overall safety and collision avoidance, and it can removing the distance between the two vehicles because they are all moving in a coordinated way. You can make them move in a smaller distance. You can improve the traffic. You can improve the road capacity, right? One such example you may have seen that if you travel at night, you may see a lot of trucks moving together, right? So the trucks usually moves in platoon because it is beneficial for them and for various regions. So such kind of system can also be deployed for an actual normal parcel travel, right? Uh, but there is a very critical part of it, right? Vehicle communication is a very critical part vehicle platooning. So if I see that there is a two-way relation between the two, right? Not only the vehicular communication is needed for vehicle platooning. So because your vehicle want to move close to each other, so when you decrease the distance, right? Usually there is a minimum distance you has to keep so that if the other front vehicle stops, you can stop your vehicle in a time. But if you want to decrease that distance, this basically means that you have to know what the other person is going to do beforehand so that you can react that way. So vehicular communication is actually needed if you want vehicular platform to come into picture. That is one way. Other aspect is that vehicle platooning can actually help also in vehicular communication. So when vehicles are moving close by, their distance decreases. So you can guarantee that there is such kind of reliability because signal power decreases with distance. So you can say that if distance is small, you can also communicate to each other efficiently. Right. Similarly, the platoon can have a leader which is coordinating the platoon movement. Such leader can actually help also in communicating with the infrastructure. For example, if one vehicle is not able to connect to the base station, not able to get the data, the platoons can actually help and give the data. So there's a very nice relation between vehicular platooning and vehicular communication, and we wanted to understand that what can be the interrelation between these two technologies, whether one can improve the other or the other ways around. Right. So our aim was to understand that if we use vehicle communication platforms together, how much it can improve and what will be the performance of such networks, right? So there has been in the past there have been some demonstration. I've listed some of them here in the slide where people have tried implementing platooning at various test levels. Right, there's a European truck platooning challenge in 2016. Japan also has a government-funded truck platooning which they have been trying. Right, so along with some other applications there, and people have also studied vehicular platooning with various communication technologies like cellular V2X or new standards like IEEE 802.11p. So they have tried and understand this, what can be the effect of platooning over vehicular communication. Right. So all these studies were mainly either experimental or simulation-based studies, and sometimes they may have focused on more on the traffic than the vehicular communication. Our goal was to actually develop some kind of analysis for that, right? So what I mean is there is a simulation where you can run the system, run a simulation over a computer, and then you can verify the performances. Then there is another aspect where you actually derive expressions and mathematically you can see what will be the what will be the actual relation between the performance and various system parameters. So we want to actually understand this more fundamental level. We want to highlight whether one variable is good, one system variable like design, like for example, platooning radius. How large you should form platoons, how many vehicles should be there in the platoon. So these are some design parameters, and I want to see the performance expression in terms of these parameters. I want to understand whether the variable is increasing or decreasing. Right, such kind of insight, if you want to develop, you would require some kind of analytical framework, mathematical framework, where these things can be shown. So we want to, yeah. So right. So that was my our aim, and to understand that there are various mathematical tools available. What we used is actually a tool in stochastic geometry, because our network actually consists of, if you look at the complete network, it consists of a lot of vehicles. Those vehicles are moving in platoons. There are multiple routes they are moving on. Then there are base stations spread over the network. So when you look at a large scale network, the geometry is very important. Like how these roads are located, where the vehicles are located. These play a very critical role in the performance. Stochastic geometry is actually a mathematical tool to study the geometry, the effect of geometry in the networks, especially when the geometry is actually random. So, so let's look at this one, the need for analysis, right? So, why do we need actually analytical framework? We need analytical framework because uh, right. Sometimes simulation is not sufficient. We will cover that. Simulation can give you results for a specific parameter, for a specific value, but if you want to look at how things are changing, you need to run the simulation for multiple times. It might create problem. Right. So that is why we do require some kind of expressions to look at. So, for when we talk about this analysis, there are different ways people look at system performance. For example, you just may be aware of there is a transmitter and there is a receiver, and you want to look at the performance of such kind of a simple link. What do? You basically can do the bit error rate characterization where you transmit some bits and evaluate how many bits are wrong. You can apply some kind of modulation and look at the performance of your modulation techniques. Right? You can talk about the capacity of a network and similarly. Right. But when we talk about networks, right, where there are multiple transmitter and receivers, things become a little bit more complicated because you have to also talk about, first of all, which transmitter you want to connect. Because now there are multiple transmitter, multiple user, which user will connect to which transmitter. Right, like in a cellular network, if your mobile can choose what base station it connects to, it can choose the connection which is closest to it. So that kind of effect you also need to include. If users move, the base station association may change. This kind of thing you also need to include. Right. So similarly, there will be interference also. In a single link, we usually don't worry about the interference, but when we have multiple links, you have to also see the effect of interference. Whether it is, if interference is large, it will also affect your performance. And many of these things depends on network geometry because the path loss, the actual power you receive depends on how far the transmitter is. If you use antennas, the gain of the antenna actually depends on the geometry. So there are multiple things you have to worry about in such setting, right? So, right. So let's look at a very simple case why this will be important, right? So let's assume there is a receiver and there are multiple transmitters. Receiver select this particular base station TX0, right? And so this will be transmitting the signal power to it. Then there is lot of uh, other transmitter which are also transmitting that will create interference to this one. Right? So total interference will be summation of the power from all the interfering base station. So PR0 is the desired power and the I is the interference. Right? And again, this receive power depends on a lot of factors, right? You know, in a typical wireless link is affected by, if you want to look at the receive power, it depends on transmit power, which is attenuated by a path loss, which is proportional to distance to power minus alpha. Alpha is some coefficient depending on the environment. There's a H fading, which is also a random variable, and shadowing also a random variable. So receive power is actually a multiplication of all these factors. You can see H, G, are random, and if the receivers and transmitters are also located randomly, the distance is also random. Right? So the interference again will be summation of all those variables. You can see how many random variables are there. For every link, there is H, G, and R, right? And there are so many links or so many variables. So if I talk about the signal to interference plus noise ratio SINR, this will be given by S plus I plus N, and each one is a random variable. So overall, the thing is random. So you cannot say that SINR is a particular value. You can directly say that SINR is a random variable. It can sometimes be large, sometimes can be small. So you have to compute the signal power accordingly. Right. So now, right. So then we talk about the performance of such systems, SINR, right? So signal to noise plus interference ratio. Then there is a that you have to evaluate. And then, or you can talk about the rate also, but you know the rate is also dependent on the SINR. So that is another thing you can compute. But if you know SINR, you can also compute the SINR in the sorry, if you know SINR, you can also compute the rate by simply shining theorem. So SINR is actually key metric which you have to worry about. And as I said, SINR is not a random variable. SINR is actually, sorry, SINR is not deterministic, it's a random variable. So you have to talk about the distribution of SINR and the rate. Right. So these things are also important here. Right, right. So what we want to, when we talk about the performance of this, we can look at something called SINR distribution, probability that SINR is above some threshold T, right? And so this threshold may be like 10 dB. You can say that want to find out what is the probability that SINR is above 10 dB. Right, and that threshold actually depends on your target. For example, if you want to support some video application, you may would like SINR threshold to be high, like 20 dB. But if you want to just support some calling feature, right, or text messaging, you would like SINR threshold to be zero because you just worry about whether a SINR is above 0 dB or not. So depending on the target application, you can put threshold and then you can ask question right? What is the probability that assigner of any link is above that threshold, right? So let's look at how difficult this problem is. If you look at a very simple system where you have some three base stations and you put a mobile in between, right? And then you want to find out how much is the distance, how much is the assigner of this mobile. So mobile is located at XY location, then there are three base stations. One is at the origin, 0, one is at minus A, and one is at plus A. So suppose the mobile is in between cell and the serving, it will connect to the middle one, the B3 base station. The serving power will be given by this S. There's a fading and then there's a distance. Similarly, interference will come from rest of the base station B2, B4, which is this one. And if I want to ask that, what is the guarantee that the assigner is above 10 dB? If I ask you to compute this, you can see it is very complicated because there are H0, H1, H2, X, and Y. Total five random variables are there. So if you want to evaluate this, this will be very difficult. That is one reason people have not been doing analysis for a longer time. They were just relying on simulation. The other factor is if you look at rate, right? In a cellular network, from channel, rate is given by the bandwidth multiplied log 1 plus SINR. Now, the bandwidth is base station bandwidth is divided among users. So, if there are n number of users for each base station, the total bandwidth available is B by n. So, the rate is actually B by n, which is per user available bandwidth multiplied by log 1 plus SIN. Now, this load is also random because this depends on user distribution. Sometimes there can be more users, sometimes there can be less number of users. Base stations also, some base stations can be large, has large cell, some base station can have a smaller area. So depending on that, the load is also random. So if you want to compute the probability that the rate is above some threshold, like 1 Mbps, is actually a very difficult problem to solve because there are large number of random variables. So what people do is they usually resort to simulations. Okay. But so they take this kind of hexagonal cell and try to compute this. But there are multiple problems with the simulation approach. As I said, you can run a system, you can get its performance, but it will not tell you how the variables are changing with time. So that's why when I say that there is a need for analysis, and as I told you that you can use stochastic geometry tools to study that, which is one of the area we also work on. So what is stochastic geometry? It's basically study of distribution, spatial distribution, which means how the objects are spread over a network or in space.
Sir, voice is not clear, sir.
Now you can hear or not?
Yeah.
Okay, so yeah, stochastic geometry has multiple concepts. One is point processes, which talks about how the points are located, which mean points can be like nodes, wireless nodes, or base stations, or vehicles. So how nodes are located, they may be located uniformly everywhere, they can be clustered, or they may be sometime there at some location they are more, some location they are less. So there are different type of configuration which you can represent using this point processes. It's like a random process. Then the other concept is this germ and grain model, which basically vehicle networks and sensor networks, millimeter wave networks, terahertz. So it's a lot of interesting application, and as the networks are changing every day, then also this is very interesting how stochastic geometry can be used. Right. So uh, just a small basic on that to help you understand what stochastic geometry is. So, suppose the points are located in a space, they're randomly located. So, there is a specific point process which is properly used, it's called Poisson point process. Here, the points are independently located in the space, which means if I take any area, two areas, A and B, then points in A and A and points in the set B, they are independent to each other. Second thing is in an area, if I look at any area A, number of points is given by they are Poisson distributed, and their mean number is the mean number is actually given by A. Sorry, the mean number of points in the area is proportional to the area of A. So bigger area and then bigger, more number of points, but the number of points are random and they are randomly distributed, right? So there is independence across points, which means the points are deployed independently, which makes this process a little bit easier to understand. Uh, right. So, how do we understand this point process? Like, you know that random variables, if you talk about random variables, you can model random variables using, you can talk, when I say that, can you characterize this random variable? So, you basically say that the random variable have a PDF or a CDF, right? And they have a PDF, CDF, or the PMF or Laplace transform. There are various ways you can talk about the distribution. So same way, random processes, you can talk about autocorrelation, the mean, these kind of things. So similarly, in point processes, there is something called void probability, which basically says that probability that there is no point in a set A, right? Because we are talking about points. There are points everywhere. So we can characterize them saying that how many points are there in the set, what is the probability there is no point in that set, right? And it's very useful. So how do we compute for PPP? Suppose there is an area A, then recall that I've just told you in any area A, number of points are Poisson distributed with mean lambda A, right? Here lambda is the density, basically tells you how many base stations are there in per unit area. So you take the area and multiply by density, how many base stations. So there are 10 base stations per meter square and the area is 100. There will be 1,000 base stations in 100 meters square area. So we compute that, then the number of points will be Poisson distributed. So probability that there is no point is given by probability that NA is 0 and NA is Poisson. Remember, for Poisson distribution, if it has a mean M, probability that it is 0 is e to power minus M. Right? This is coming from the distribution of NA. That probability that NA is 0 is exponential minus lambda A. Right? Here, as I said, lambda is base station density of base station. So if you want to compute void probability, you compute area. E to power lambda into area is your void probability, which means there will not be any point here. Right. So let's look at how we can use that in a simple network. Right. I'll just give you an example. Suppose there is a network with where base stations are many base stations, they are distributed as a Poisson point process. Then you have a user, mobile user. It want to connect to the base station. So it connects to the closest base station. Right. So I want to ask, because the SNR will depend on the power from this base station. The base station is connected to. So I want to ask how far the base station is, because that will determine the power. So let's call it R. So what is the distance of this base station, which we call serving distance? Serving distance R is basically distance of the closest base station which you are connected to. So This is a random variable because base stations are randomly located. So sometimes the base station can be close by, sometimes they can be a tower close to you. Sometimes for other users, tower can be far away. So probability that your tower is more than a distance away is basically given by probability that there is no base station in a circle of radius a. Right. Is that clear? So probability that your base station, serving base station is more than a. Remember, it is the closest base station. So there cannot be any other base station closer than it. So a serving base station can be more than a away only if there is no other base station closer to a, closer than a. Right. And if I want to compute the probability that there is no base station within the ball of a, that will be given by e to power minus lambda into this area of A, which is pi A square. So it will be given by e to power minus lambda pi A square. Right. So this is the distribution of serving. Now SNR is what? SNR is given by the power divided by sigma square. Right. So if I want to compute the SNR, I need to compute the probability that SNR is above the threshold. Right. Now if I put the SNR value, which is R minus alpha upon sigma square, I get R is less than gamma sigma square to power minus 1. Now we know the distribution of R. If I put the distribution of R, I get this value. So you can see that I can actually compute the SNR distribution. I can actually plot it, and if someone asks me how much density we should allow so that SNR is above 10 dB 90% of time, we can answer such kind of questions. So here we have not included the effect of interference, but that can also be included, right? There is something called this theorem, which says that if you have any function f and you want to go to every point and compute the value of function and then sum the value. So there is a function, you go to every point, evaluate that function, and then sum over all points. Now this is a random variable because points are randomly. So you can compute this by computing as 1 second. Yeah. So So if you want to, so you take a function, go to every point, and you sum them, and then you ask, this as is a random variable because points are random. You ask what is the expected value of s, mean value of s. So you can compute the mean by doing the integration of the function and multiply by lambda. Right. This is known as Campbell theorem, which is very much useful. And why we are doing this? Because you can compute the effect of interference. So up till now we have only talked about SNR. If you also want to include the interference, you need to include this also. Right. So how can you do that? Consider a network with base station distributed as Poisson point process. If you take a user at the origin, the interference at the user is basically you need to sum the power from all the base stations. From each base station, the power is hi and divided by the path loss, right? So if you sum this was exactly like the form we covered last time, summation of values of a function at different xi. So I can apply this Campbell theorem, and from there I can compute the mean of I. Right? So I can not only I can talk about SNR, I can also include the effect of mean interference into it, right? And then I would not go much into that, but you can also talk about the not just the mean, the distribution of S also, right? So there is also for PPP there is also expressions available which we can use to compute the distribution. And remember, interference can be written in this form, so you can also compute a distribution of the interference. So stochastic geometry, you can use them to compute a distribution of SNR, distribution of interference, and distribution of SINR in a large network, not just small network, which means I'm not just talking about one link to another link. I'm talking about a very large network which has multiple transmitter, receiver, blockages, right, and everything in it. Right, so it's become very popular, which have people have used over time. Right. So let's come back to the with this one give you some background on what has happened, what tool we are using. But let's come back to our original problem where we want to study the vehicular communication with platoon networks. Right. So our goal is actually, as I said, I want to develop a mathematical framework which can study various which can study various components of vehicular networks. What are the components? There are roads, right? On roads, there are platoons. On platoons, there are multiple vehicles. Then there are multiple base stations. The base stations are communicating to vehicles. Vehicles are communicating to each other or the platoon leader, right? We want to include all these effects, right? And then understand when we include all this effect, we want to understand the impact of how the how the platoon radius is affecting performance, how the density of the platoons is affecting performance, how the number of total vehicles on the road is affecting our performance. So these kind of things we want to look at, along with the coexistence of previous technologies like Wi-Fi, cellular. These things we also want to look at. Right. So why the problem is interesting? You can see that when the vehicles are not moving in platoon, they are moving independently. Like if you look at one base station, the all the vehicles are coming randomly. So the load is actually distributed uniformly over the network, which means anytime the vehicle can connect some base station. So usually all base stations are active and they have some number of users. Now, if you look at the platoon network, where vehicles are moving in platoon, so when they're moving together, it may happen that there is no platoon, so there is no user, and suddenly a platoon comes, so there's a lot of users come. Right? So it can actually happen that there is a bursty traffic at the base station. Sometimes base station is just running idle, and sometimes a lot of vehicles come in the platoon. So the base station get a lot of load. Right? This load can affect the rate coverage. So our goal was first to understand what is the probability that vehicle is having a base station is having K vehicle as its load. It has to serve K vehicles. Like this is from a service provider perspective that if you want to design a network for vehicles, you have to make sure that your system doesn't go to overload. So if you know the probability that your system can become has more than 10 vehicle load, then you can design your system that way. The second thing is what is average load on the base station. This will help us to decide how much each base station will get bandwidth, how much each vehicle will get, and that will affect us do the resource allocation properly. Right. Now, if there is no vehicle connected to any base station, at that time, base station can turn off some of its operation to save energy. Right. If there's a large probability that there is only few base station will be active and other base station will be turned off, such kind of policies can improve the energy efficiency significantly. So we want to look at the probability that there is no load at the base station, and that is from the energy efficiency perspective. You can reduce interference, you can reduce the power, serving power. So you can become a cost-effective solution. Then what is the probability that a base station is serving a single vehicle? So this means the vehicle is on, so a base station is on, so you are wasting energy, but there is only one vehicle connected to this base station. So basically you are wasting energy. It will be better if we turn off the base station, offload the user to someone else. So this is from the resource perspective again. And then at the last point, from the user perspective, the vehicle. Vehicle main goal is to receive data, to maybe watch movie or hear songs, listen to songs, or maybe to get some critical map data or alerts data. So from its perspective, what is the probability that it can receive for say let's more than 1 Mbps, right? That is for rate coverage of the vehicle, and that is from the user perspective. So there are multiple questions we would like to answer in this study, right? And like let's look at how they are being affected in this, right? So We want to look at from base station perspective, the average load on a base station, from the vehicle perspective, what is the rate coverage, that includes the effect of load and how many base stations are active. So all these factors are being combined together. Right. So now let's look at how do we move model vehicles, or how do we model platoon vehicles. Right. So if let's talk about a single road, if the vehicles are moving on a straight road, uh, then at any time they can be seen as random points on the road because they are not talking to each other. So their movement is independent. Sometimes these vehicles can be close by, sometimes they can be very large distance between the vehicles. So these vehicles can be modeled using the Poisson point process. I have described you what the Poisson point process is, right? It basically has this property that if you take any interval, number of points in that are Poisson distributed, and if you talk about the points at two different locations, they are independent to each other. So this independence property is very helpful. It simplifies the analysis by a significant amount. That's one more reason the to the popularity of the Poisson point process. Right. So here you have two levels. So that was independent, but now you have two level of analysis. On each road, you have platoons, and then on the platoons, inside the platoons, you have vehicles, right? So this two level of randomness, how do we model? Right? So one way which we did was you can assume that the platoons are PPP, and then inside platoons, the vehicles are also distributed as a finite PPP, which means a bounded PPP. Right. So such kind of setup can be created. You can see this red points are the platoon centers. So we first say that platoon centers are PPP with some density, and then around each platoon center there is a area region of A by 2 both sides, which defines the extent of the platoon. And then inside that platoon, there are many vehicles which are also located randomly as a PPP that are denoted by blue points. But now these vehicles are bound to remain in that region, so it's a finite PPP. Right. If I combine all these blue dots, I will get a process which we call Martin cluster point process. It's a cluster point process because you can see it's creating the clusters of point. And such kind of process can be used to model the location of the vehicles. Right. So that is what we are interested in. Maybe I can skip that. Right. So we want to compare two scenarios. One we call ITS, independent traffic scenario, where vehicles are moving independently. And the second thing we want to talk about scenario, which called platoon traffic scenario, where the vehicles are moving in platoons. And we want to understand what is the effect of such kind of movement. For network perspective, there are base stations, right? So their base stations are also randomly distributed around the road. So you can call it roadside units. That is same in both scenarios. Now we want to look at when the vehicles move in the platoon, what will be the load of the base station, right? Here you can see also when the vehicles are moving independently in the ITS scenario, uh, sorry, in the ITS, usually the vehicles are everywhere. So each base station has having some load, some has less and some has more. When they move in platoons, it may happen that one base station has no vehicle while the other has a lot of vehicles. So it makes the load little bit asymmetric and bursty, which need to be thought of. Right. Okay, so maybe I will not go to the math lot of thing, but you can actually compute effectively the load of the on each base station. Like the way to compute it, first find out what will be the length of each of the cell, which is given by this distribution is an exponentially distribution, and then from it's a gamma distribution, and from there you can compute how many of the users are located in the inside cell. That is also random. And combining the two, you can actually get the scenario. Same thing you can do with the platoons also, right? So that will give me the load on the typical cell, right? So I would like to at least clarify this point. There are two type of cells in our analysis. One is you pick one base station randomly. So there are many base stations. You pick one base station like this, and then for example, I picked this base station, and then I look at this base station only. How many vehicles are there? So there are maybe multiple roads on that. There may be vehicle platoons, and I ask how many vehicles are there. Right, that's called typical load. Right, it's a load on the typical base station. There is one more thing called tagged base station. Right. So how that comes? So here you pick the vehicle, not the base station. You pick one vehicle randomly, and then you ask which base station this vehicle is connected to, and then you basically talk about the uh, this cell, right? So here I have picked one. Out of all these vehicles, I picked one vehicle and look at its cell and talk about what is the load on this cell, right? Usually, tagged cell is bigger than typical cell because when you are picking one vehicle, you usually pick the vehicle from a large cell because there are more number of users there. Right. So we need to characterize both loads, right, and which are helpful in our distribution. So this there's the same way we can do this also. There we can know the load of the tag cell, and from there we can compute the how many platoons are there, from then how many vehicles are there. This can be computed. Right. And when we plotted that, we saw that the same thing which we were expecting is we saw that in platoon traffic scenario, there is usually a higher load. Sorry. So in platoon traffic scenario, there is usually a higher load on each base station because the vehicles are moving. The main load is same, but the variance is more, which means that they can be higher, they can be load bursty in this traffic scenarios. Right? So variance of load distribution in PTS is higher. But one thing is also interesting that off probability is also high, which means probability that there is no vehicle in a base station is also high, which means you can turn off that base station. And that can result in an energy efficiency of the base station. Right, so here you can see the P of probability that the base station has no vehicle, which means I can turn off the base station. So it's also high in the PTS, which basically says that you can basically turn off the base station, so you can save energy and only turn on those base stations where the traffic is. Right. Okay, so then we talk about rate coverage. As I said, rate coverage is the probability that rate at any typical user is more than certain threshold, right? So the interesting thing is it depends on, for example, here, this is the rate, B is the total bandwidth, M is the load, and log 1 plus SINR is the SINR of that. Now, it affects on the load, which means how many users are there in the tag cell, in the cell you have been connected to, how many other users are there. So you require the load of the tag cell. Similarly, in SINR, you have the interference from all base stations. But the base stations which are off, they are not contributing any interference. So that will improve our interference, that will reduce our interference, which means that I also need to know what is the probability that the base station is off. Only the on base stations are creating interference. So that is computed from knowing the load on the each base station. So I need both of them, and both of them affect our performance, right? In two ways. The load on that each base station has no vehicle, that is also important, and the average or the distribution of how many vehicles are there also affect our rate allocation, the bandwidth allocation. So there are two ways this load can affect our performance. Right. Now, this was on a single road. We asked about how I can extend this for multiple roads. Right. So here there is one more additional factor. Right. There is a three level of randomness. Earlier there were two. That there are platoons and the platoon there is a vehicle. Now this platoons are located on on roads. Those roads can also be random. So how do we model this irregularity in the road layout? So if you look at a typical network, like this is a snapshot from Google Maps showing a typical road, which is really random. So there are multiple ways people have talked about this one. One is called random linear graph. This one is Poisson-Warnite tesselation, where you can model the roads. Right. There is also called a Poisson line tesselation, right, which we actually use. Like the way it is that it's a process which shows how the lines are located, right? And that is how so we model the roads as a Poisson line process where every line is modeled using two parameters, right? The distance from the origin and the angle of the line. From there we model this and use that our process, right? So adjusting the different orientation and the different distribution, you can get different type of layouts. Like for first layout is called Warnite, is called Poisson line process, and the second one is called Manhattan process, which only have horizontal and vertical directions. So you can get different layouts of the vehicle of the roads, and then you can use them to create the overall traffic. So what we use that we proposed a novel method saying that we will be moving modeling lines as a Poisson line process. In the line, there will be platoons, which are PPP, and then inside platoon, there will be vehicle, which will be finite PPP. So there's three level of randomness. This point process is actually triply stochastic, which we have modeled and we have analyzed them for performances. Right. So this is how it will look like. That there are multiple roads you can see, and each road there are these platoons, and inside platoon there are vehicles, and then there are multiple base stations. This circle you are seeing, these are base station, and then each base station has a area around it, at cell around it, where only it is serving the vehicles. So vehicle which fall inside the area, it has to serve. Right. So what is the key takeaway we got it from here is that although it is true that if I just plot the sorry, yeah, if I just plot the uh, rate coverage with base station density, right? How many base stations are there? So we saw that definitely that the ITS, non-Platoon's network, is giving you better coverage because it has a more uniform distribution of base, more uniform distribution of U vehicles, right? But it also has a very large it also has a very large off probability, which means a lot of base station may be turned off because of the irregularity. So what we did was we plotted with the active base station density, right? Not just the regular base station. We just worried about how many base stations which are active, which define the energy of the overall consumption. With that, we plot and we found that if I keep my active base station density constant, then platoon traffic is giving me a better efficiency because with less number of base station is can serve more number of vehicles, can provide you better coverage. Right. So it can be actually helpful. Right. So I would like to make a point that platoon traffic is not exactly from the point of coverage. It is mainly from the point of improving the traffic congestion, like the actual transportation traffic congestion. But we show that it can actually also get very nice rate coverage because of its energy efficient operations. Right. So, what else this Platoon network can help us, right? So that's what we call Platoon assisted communication, right? So in a typical V2X network, if I look at member vehicles, the normal vehicles usually connect to infrastructures to obtain either traffic safety data, informant data or entertainment or some information they require or some kind of critical alerts they are looking for. Right. So in such cases, platoon leader. So every platoon has a leader which is coordinating among vehicles. It can actually help in establishing this V2I link, which can complement the V2X link. So a vehicle is trying to connect to the infrastructure, but that link is not being established. Then the platoon head can establish the link by himself and then offload the data to the vehicle. Right. So we talked about such kind of this architecture where you have platoon assisted communication. There is a direct connection, which means if a base station is closer to the vehicle, it will directly connect to the base station. But if the base station is far away, the vehicle will connect to its platoon leader, and the platoon leader will connect to the base station. So such platoon leaders can help establish the communication. The main intuition I would expect is that platoon leader is usually better equipped, so the communication link performance is better for platoon leader compared to a regular vehicle, right? This way, you don't need to equip every platoon, every vehicle as having full-fledged communication capability. They can just communicate to platoon leader, and the platoon leader can be very effective, can have a lot of better communication infrastructure. Right. So it's easier to maintain one connection between base station and platoon head than maintaining multiple connections between all the vehicles. Such kind of coordination can help in the practical level, right? So if a base station is connected to, in this example, there is a platoon leader which is shown by a green car, blue are the member vehicles. So base station is serving the platoon leader, and then the platoon leader is serving to the vehicle. So if you want to look at the performance, that whether this link will work or not, you have to talk about both links. The link between the platoon leader and the base station, that also need to be successful, and then the platoon leader is the vehicle. Both link need to be jointly successful. Only then the communication can be established. Right. So this is right. So this is what, and then you have to efficiently split your bandwidth because you have to also support multiple type of communication. You would like base station to talk to platoon head, platoon head to member vehicle directly to base station. So you can talk about the distribution, and from there you can get what kind of bandwidth is available to every of the user, right? So we analyze this one, and then we try to understand how the rate coverage will be affected when I change various parameters. Right. For example, the platoon radius is one crucial example. Right. Whether each platoon should be 100 meters or 200 meters, that is the one crucial information. So we saw that there are two type of links. One is base station to the vehicle direct, and the other one is via platoon leader, which is base station talks to platoon head talks to the vehicle. So what we saw that this red curve is showing the coverage via platoon leader, the green one is showing the direct coverage, and the blue one is the sum of the two. So as I change my platoon radius, everything else is same. The network load is same, which means that average number of vehicles on the road is same, number of base stations are same. Then we found that as you increase the platoon radius significantly, the vehicle is moving away from the platoon leader. So platoon leader will have difficulty communicating with the vehicle. So in that case, this coverage via platoon head will decrease with A. But on the other hand, when base stations are moving away, sorry, when the vehicles are platoon leader is moving away from the vehicles, then the base station communication can actually improve, which means they will be increased in the direct coverage, right? And the total summation will actually have a trade-off, which will mean there is some platoon radius where none of them is good. You should avoid that. You should either have a smaller platoons or a larger platoons, and then also between the two, smaller platoons are actually more useful because they are able to capture that lack of link, loss of link between base station and vehicle, efficiently, which means it will only shift if the platoon meter is very close. Otherwise, it will not disturb the performance. Right. So we have other performance evaluation we also did to understand various different aspects of the communication, right? So this kind of work has multiple aspects of the performance, not just one. For example, what is the load distribution? What is the rate coverage performance? What is the joint performance? How do you establish different rates? So there are different papers I have listed here, which we have talked about various aspects of the communication. Right? If you are interested, you can look over those. This is actually a joint work with my students, Kaushleen and Kanak Raju, and also with Professor Dylan from Virginia Tech. Right. So, right. So with this, I kind of finished my presentation. Right. And I would just like to say that. So our group actually works on more interesting topics related to this one also. Up to now, for when we talk about 5G, like the current scenario, we have been working on like this device-to-device network, ad hoc networks that we're talking, which I presented in today's class about vehicle communication, platoon-based architecture. We also work on spectrum sharing in cognitive radio. For example, how can you can improve if there are multiple technologies together from a perspective of vehicular systems or other systems also. Right. We also look at cyber physical systems and heterogeneous systems where you have multiple type of base stations. Right. How do we split the load between those? How do we perform? How do we compute performance evaluation? This kind of thing we have looked at. But when we look at more modern applications, like what the things will be interesting in the future, right? We also look at various new aspects like terahertz networks, which where we talk about how to model such channels, right? How to analyze the impact of various scatters and various blockages on the performances. We also work on satellite communication performances. We had done some work on machine learning in wireless also. Another area we look at is RIS, which is reconfigurable surface, and we mainly focus on how to design systems where should you put RIS, right? Because RIS is also a very geometric construct. If you don't place it properly, you will not get good coverage. So where do we put it? Yeah, other than that, we also work on visible light and quantum communication. Right, we look at from more information theory perspective. We have been also working on UAV and non-terrestrial networks. Right. One other interesting area we look at is called molecular communication, where we actually communicate via molecules. Right. So it's a different than typical RF communication where you communicate via RF. Here we actually do communication with the help of molecules. Right. So these are very interesting problems where our group works on. Right. And thanks to all of my students who have been working on this one. Right. So if you're more interested, you can go through the group website and look at our group's work, or you can contact me and about any questions on this one. Right. So with this, I conclude my presentation. If you have any questions, you can ask me. Thank you.
Audience, if you have any questions, you can ask.
Sir, why do they go for this Poisson's distribution and why not Gaussian distribution, sir, in this aspect?
So Gaussian distribution is you have to define what exactly means from this point perspective, because Gaussian is a random variable distribution. And here we are talking about the point process, which means the distribution of points around the space. Right. So number of points is a discrete random variable, right? Which means you can use so Gaussian is a continuous random variable, and Poisson point is a discrete. So you're talking about distribution of how many points are there in a set. So you need something which is a discrete random variable. You can use binomial distribution, you can use Poisson distribution, or uniform distribution. Any discrete random variable you can use to depict how many points are there.
Okay, sir, thank you.
Sometimes we do use Gaussian in other way. For example, if I want to depict that there is many base station at the center and far away there are less number of this one, I can put the average number of base station like the density as a function of location. And the density I can take as a Gaussian function for.
Sir, will there be any fixed number of performance metrics, or will it be changing based on the application?
Right. So there is some metrics we do look at, like as I talked about rate coverage, is how much rate you are getting, the distribution of that, signer distribution. Sometimes we look at the throughput, which means how many bits you are sending in a particular area. Right. This thing application you can look at, but exactly this equation changes based on the application also. Right. I mean, you may be interested in latency, you may be interested in rate, you may be interested how the bandwidth is allocated, you may be interested in more about a combined matrix which may take latency and the throughput together. So the application can change based on what you are looking at, but it usually is a variant of these fundamental metrics like rate distribution, assigner distribution, load distribution, these kind of metrics.
Okay, sir. Thank you.
So any other queries?
Okay. So if you're interested in stochastic geometry more, there is a tutorial I have written. It's available on our website. You can go to the website and look at. There's a called primer on stochastic geometry for cellular networks. You can look at if you're interested in this one. Otherwise, if you're interested in any of the research works, you can look at. I usually put papers on the website, so you should be okay to read any paper you're interested in.
Then you can conclude the session.
Okay, sir. I'd like to thank Dr. Gupta, sir, for an exceptionally enriching and thought-provoking session. Your insights to model random events using Poisson's distribution to locate the vehicle, message arrivals, and interference patterns, connecting with V2X technologies, analyzing standard deviations and variance, have truly broadened our perspective. We are deeply grateful for your time, expertise, and inspiring presence with us today. Thank you very much, sir.
Okay. Thank you for listening to me, and
Thank you, sir.
okay, bye.
So participants, you can leave now. Again, you join by 3:30.